Okay, so yesterday we talked a little bit about um, redox, and that was a lot of review. Today, when we do our lecture, it's going to be a lot of new stuff. Um, and there's a real strong emphasis in AP chemistry on the acid, base, and moving forward. And today is going to serve as an introduction to that. So you're going to want to make sure that you really understand these definitions that are listed here and how to identify some of these different things. This just goes back to probably a review maybe in ninth grade or even middle school. They always talk about acids as kind of having a sour taste. And vinegar, citric acid, and citrus fruits would be a good example of that. Bases tend to taste bitter. So if you don't like broccoli, you can use the defense that you're using like a dilute sort of drain cleaner is giving it that bitter, icky taste to it. I happen to love broccoli. But a lot of the poisonous plants will have a strong base, and usually that is sort of natural for us to shy away from that. It's one of the reasons kids who have really good sense of taste tend not to like their broccoli and turnips and some of the vegetables along those lines. Now, when they say feel slippery, this is really a good indication if you're working with a base. If your hands feel slippery, it's reacting with the oils in your skin, and it actually makes a soap molecule. Things that have ammonia in them tend to be bases. Your blood has a slightly higher than 7 pH, and like I mentioned before, drain cleaner is a really strong base. So there's a lot of different ways you could define acids. And Arrhenius acid and bases will dissociate in water to produce hydrogen ions. And as you can see here, we use this abbreviation HA for a given acid. Will dissociate into the ions H+. And if you make that H+ ion, we really associate that being an acid. Bases, we think of OH. All right, so this is really important. Circle this and highlight it or whatever, but H+ for acid, OH- for base. You can see the abbreviations A and B are going to be used in a lot of these examples. Now, there is a problem with the Arrhenius definition, and that is that it's only true for if they have a hydroxide ions. And there are a lot of bases that do not have hydroxide ions, but yet they still form basic solutions when added to water. So that's why we have to kind of expand our definition a little bit. And here's a little better and more complete definition. If you're asked, what is probably a better definition, this is definitely it. Bronsted, Lowry, acids and bases. Acids donate protons. Bases accept protons. Because the protons are always going to come into play. It's not acid-base chemistry if you're not exchanging a proton. And I would like you to note that the symbol for proton is hydrogen, which is normally a proton and an electron with a plus charge. So clearly that then would be defined as just a proton because the electron is gone. So bases will sop up or kind of mop up those hydrogen ions, and they can make them disappear from solutions. All right. So that means that when we talk about these reactions, the old Ha right here, the acid, can donate its hydrogen. And then when it does that, it becomes A minus. Now, if you think about this, if you look at this double arrow in this reaction can go both ways. So therefore, this product of the acid is now a base because it could accept a proton to become HA, just go in the other direction. Okay? So that should make a lot of sense to you. So this acid makes a conjugate base of HA. This base in the reaction, you can see it picked up a hydrogen. Well, guess what? Over here on the right side, it now has a hydrogen that it can donate, making it an acid. And we usually use the term conjugate acid for defining that. So this is the conjugate acid. Whoop! What happened here? Hello. This is the conjugate acid of that base. You can see they're paired up. So that's a Bronsted-Lowry reaction. So you have to look at a chemical. I love this question up here. What is what here? Sounds like a very philosophical question, but it's simply asking you to label where are the acids, where are the bases, conjugate acids, conjugate bases. So just to see where you're at with this, see if you can look at this right now and label. Everything on the left side has to be either an acid or a base, and on the right side it has to be a conjugate acid or a conjugate base. So why don't you see if you can do all 8 of these and label them and see how you do. So go ahead and hit the pause. Doot. Welcome back. Let's see how you did. Okay, so in this first one here, HNO3, or HNO2, not a super common acid, but definitely is donating its hydrogen here. And a lot of times that hydrogen will be an indication of being an acid, like HCl, H2SO4, and those things. But the water here, you can see, picks up the hydrogen and becomes this hydronium ion. These are going to be really common in acid-base chemistry. That makes this the conjugate base because it can now accept a hydrogen. So it was the acid, so this is paired up. So the green is paired with green here, if you want to color code your notes. And this base picked up a hydrogen. And now look at this. This is a really nice, strong acid. And is perfectly willing to, as you know, water doesn't usually exist as H3O+, so it's going to want to give up that hydrogen. So this is definitely a reversible reaction. And hopefully you figured out on the second one that it was kind of flip-flopped. So what happens here is that this nitrogen picked up a hydrogen to become ammonium. So this is ammonia, that's ammonium. Therefore, you're pairing those up, red with red, base, conjugate acid, acid, conjugate base. You betcha. Those terms right there, you betcha. H3O+, you think of acid. OH-, you better think of base. And this shows you that water can act as both an acid or a base. The actual vocabulary word is not in our curriculum, but if you're interested, it's amphoteric, like amphibian, and being able to act as both. So water can be either an acid or a base. That's just kind of an important thing to note here. Okay, so we're going to note as this previous slide here introduces how important water is, and this can kind of show you that water can do this, little Lewis dot structure there to clarify what's going on, and you got this H3O plus, or it can actually not that uncommon for that hydrogen to come off of there. And when you drink water, there's some of this in there, and there's some of that in there, guaranteed. As a matter of fact, about 1 times 10 to the minus 7 moles per liter of this and of that. Okay, so we're going to figure that stuff out as we move forward as well. So understanding that how water does this is pretty important. Okay, so you want to think of these things as conjugate acid-base pairs. All right, so that HA that we talked about is paired as a conjugate acid-base pair. So this is just really expanding on something that they talked about previously. All right, now it is very important that we understand and recognize a strong acid and a weak acid, and that they're going to behave differently. For example, in defining a strong acid, so if HA was a strong acid, remember A is a variable, so depending on what that is, we'll be able to predict whether it's a strong acid or a weak acid. But a strong acid will dissociate or ionize completely in water. So this is a one-way arrow. Highlight that arrow, because that going all the way to the right is important in defining something as a strong acid. All right. Now, a weak acid, this is going to be a double arrow, and it might even, you might not form hardly any of this. There are some problems that we do where it'll be really minuscule percentages that will actually ionize at all. So really, that makes that acid not that much of a factor in an aqueous solution. So the two-way arrow with equilibrium lying over to that side. Now, we technically haven't dealt with the equilibrium constant, but this whole idea of going back and forth is going to become a lot clearer when we do equilibrium chemistry. But the bottom line is, you still have mostly this stuff. Just a few of these guys. Just a couple of them kind of broke free. Whereas this one, this is a one-way. There's none of this left. Okay? Of course, you could have excess of one of them, but that's a one-way reaction. So that's defining a strong acid. And I'm going to stop the video here and finish up on the next one.